Good morning, everybody. Let's talk math. Let's talk inverses today. And as you can see, let's talk The Sneetches by Dr. Seuss. Maybe you've heard of this story before. Maybe you've read it before. Maybe not. The Sneetches are weird yellow creatures, and they look like this. Now, checking out this picture, you can tell that this Sneetch thinks he's hot, right? And the reason he thinks he's hot is that he has this green star on his belly. Now, these three dejected Sneetches are upset because they don't have the star on their belly, right? And this is a story from Dr. Seuss, and of course it teaches us a nice moral, right? Not to covet things that other people have that are so silly that they can't control, like stars on their belly, blah, blah, blah. But what happens in this book is that this guy comes to town. He's a bit of a capitalist. He's a bit of a snob. And I believe he has a funny name as well. Sylvester McMonkey McBean. And Sylvester McMonkey McBean has a very peculiar machine. And what this machine does is it will put a star on a Sneetch's belly for $3 each. And so what happens is all of these sad Sneetches are like, I'll pay $3. Pay $3. They get the stars on their bellies, and as you can see, they are very excited. Very, very excited to now have stars on their belly. Now, unfortunately, what happens is that the Sneetches with stars on their belly decide, you know what? It's cool to not have a star on your belly anymore. So I'm going to pay this guy to go into the red machine to take off the star on my belly. I don't have any words on this second one. Now, what ends up happening in this story is that some of them want to put the stars on their belly. Some of them want to take them off. Then once they take them off, they want to put them back on. Then once they put them on, they want to take them back off. This guy's getting rich. And in the end, nobody remembers what's cool and what's not cool. Nobody remembers whether stars on your belly is a cool thing or a bad thing. And at the end of the day, we're all just Sneetches at the end, right? That's the whole idea. Now, in math, where does this come into play? I want to look at these two machines, this yellow machine and this red machine. And in math, these things are like functions, okay? What a function does is, let's say that we've got f of x is equal to 2x plus 3. If this was a function, what this is it is a machine that is going to take your number and it's going to modify it. So if we want to do f of 2, this function is going to multiply your number by 2, and then it's going to add 3 to your number. And that's going to pop out a brand new number. So we go in as a 2, we come out as a 7, because that's what our function does. Multiplies it by 2, adds it with 3. So very similar to over here, if we think about this yellow function as a mathematical function, it is altering our inputs, giving us a different output. You can see in, out. Now the red function is doing the exact opposite. The reason we're talking about the Sneetches today is that what we're talking about is inverses. And to keep it very simply, an inverse is the function that does the exact opposite of what your function does, okay? It would turn a 7 into a 2 because it would subtract the 3 and it would divide by the 2, okay? So inverse functions are the exact opposite of our regular functions. Now, the way that we figure that out is we basically, whenever it comes to inverses, if you want a little bit of definition, or maybe you have room to write this, maybe not, maybe you just want to read it. Inverses are going to basically undo each other. They're going to reverse each other, okay? So inverse functions, they're going to undo each other. We've seen inverse functions. I'll give you an example. X squared, square root x. These are inverses. Right? If you take a number and you square it and then you square root it, you're going to be right back where you were, right? So let's take 3. 3 squared is 9. Square root 9 is 3. If we put it through both machines that are inverses, nothing's going to happen, okay? It would be just like if you added one and then subtracted one. That would be inverse functions. So we've seen inverse functions before. Now, the main idea with inverses is find them by switching x and y. Okay? That is the main idea today. Everything that has to do with inverse has to do with switch your x and your y. So, if I have a function that looks like this, and it is literally just a bunch of dots, my inverse is just switch the x and the y. So the inverse would be -7, -2. I've just switched my x and my y. My inverse would be -3, -1. My inverse would be 5, 0. My inverse would be 2, 1. We can put these big squiggles on it if we want. Okay, that's a piece of cake. Switch your x and your y. No problem at all. Now, a lot of times they throw in the concept of what does it mean to be a function, right? To be a function, this is something that you learn a lot about in Algebra 1. A function has no repeated x's, right? For the functions, you've learned about the vertical line test or the pencil test, where you're going to take a vertical line and you're going to scan it across and see if you've touched your pencil at 2 points. You know, for example, it would look something like this, right? If I think about this as being a vertical line, we would go scanning, 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 scanning. Okay, well, we've never touched the line twice, so that would be a function. So, our original function has -2, -1, 0, 1. That is a function because it has no repeated x's. Our inverse has -7, -3, 5, 2. That is also a function because they both don't have repeated x values. And I don't know why they use this one-to-one function. I don't think that in Algebra 2 that is something that you need to learn. The first time I ever heard one-to-one function was in college. So I'm not sure why we've thrown this in here. But what one-to-one means is basically that you're a function originally and you are a function in your inverse. Okay? Now what that means is if you see it like this, we have no x values that are repeated. One line, one line, one line, one line. So that's good. If we go in the opposite direction and we do an inverse function, you can see that this number 1 is going out 2 places. And so this would not be a function. I don't know. Don't worry about this example. That's a little too complicated. I don't know why we're really working on that. Determine whether the graph is one-to-one. Who cares? I don't really care about that stuff. Here's what you really need to do in Algebra 2. Find the inverse of a function, okay? This function, what it does is it takes your number, it turns it negative, and then it adds 9, okay? So if I said, hey, function, you know, my initial number is a 3, it would say, okay, I will take your 3, and I will turn it negative, and then I will add 9, and the answer would be 6. In a 3, out a 6. Now, what we want to do is we want to find the opposite function, right? If we think about this as the yellow machine, we want to find the red machine. The machine that will go from a 6 to a 2. We need to find the one that would subtract the 9 and turn our number negative. And so what we do is a really easy process when it comes to inverses. Switch the x and the y. Okay, switch the x and the y, switch the x and the y. So what we need to do for this function is switch the x and the y. So we want to consider this as a y. So it will be y equals negative x plus 9. Then we're going to switch the x and the y. And it's going to be x equals negative y plus 9. Now, really importantly, we are not going to bring any of the stuff with the x or the y, right? So this negative sign here, a big mistake students make is that this negative sign ends up over here. But we're not transporting the negatives. We're only swapping the x's and the y's. And now we're almost done. We just need to solve for y again, okay? So we would want to solve for y. We would want to subtract 9. Because we're trying to isolate the y, so I would subtract 9. X minus 9 equals negative y. And then I would want to get rid of this negative sign. So I would want to maybe multiply everything by a negative, or maybe divide by -1. I would probably just multiply everything by a -1. Okay? And so when I've done that, I would get negative x plus 9 equals positive y. All right, so look at what I've got here, and maybe I'll rewrite it with the y on the left side again. Our red machine should be y equals negative x plus 9. If our yellow machine is going to... messed up. Plus 9, gotta subtract the 9, divide by negative. If our yellow machine is going to, turn it negative and add 9, what this machine should do is it should turn the 6 in to a 3 out. Now, unfortunately, that's the worst example that I've chosen because it's going to work both ways for this question. So a 6 in. Ugh. This question has just not worked out great. F of 6 is equal to negative 6 plus 9, which would be 3. There's our 6 in and our 3 out. And that should work with, these should work opposite with any number that I pick. Okay, so let me pick perhaps a better example. Okay, let's say that we're going to go in with a negative 11. Okay, so if my F is negative 11, my x is negative 11. That should be negative 11 plus 9. That's going to output negative 11 is going to be 11 plus 9, which is going to be 20. In with negative 11, out with 20. My red function should be in with 20, out with negative 11. So if I put in a 20 here, f of 20, that would be negative 20 plus 9. That would be negative 11. So you can see how these are opposite functions. They're doing the exact opposite thing to our function. We're able to basically, if one's working forward, the other one is working backwards. I just chose a really strange question there. Let's do number 7. We need to figure out what is the inverse function, okay? And so it's a really easy process. We're going to write it as a y. Once we've written it as a y, we're going to swap the x and the y. And so we should have x equals 4/3 y minus 7. And then we're going to solve for the y. We're going to try to get the y by itself. So I'm going to make some more room for myself over here. I'm just going to move it. 4/3 y minus 7. So really easy algebra 1, plus 7 on both sides. We're going to get x plus 7 equals 4/3 y. We need to get rid of this fraction. The easiest way that I always like to get rid of fractions is to multiply by the denominator first. Okay, I'm going to multiply by 3, and that's going to get rid of the 3 on the bottom. So that would be 3x plus 21 is equal to 4y. And now that I've done that, now I'm going to divide by 4. And then doing it in 2 steps like that helps me out. So I'm going to write the y on the left, right? This is canceled out. That would be y is equal to 3x plus 21 over 4. Now, one thing that I'll say is that to some degree, some of these questions you could maybe solve in your head, right? You know that the function and its inverse should have all the opposite things. So you should know that the 4/3 is going to be a 3/4. The -7 is going to be a +7. But students who try to do this in their head always make mistakes, okay? If you had made this a +7, you'd have got it wrong because it needs to be a +21. And it needs to be in the numerator, not left tagging along behind the function, right? So they're very similar. They have all the same pieces, but I'm telling you, kids who try to do this on their own always mess up. Yeah, so the whole point of the functions here is that the yellow function, the original function, and the red function, these are doing the exact opposite thing to whatever number that you put in, okay? If you put in a 5 and you get out a 10, you put in a 10, you'll get out a 5 every time. They're working exact opposites. Now, we've got all kinds of different things here. Let's just do one of these. Really quick process. Turn it into a y. Do a swap. Again, nothing goes with the swap, so the x leaves for the y, but the square root does not move. So it should still look like this, and then solve the question. Add the 5 to the other side. How do we get rid of a square root? We do a square, so we need to square both sides. And there we go. There's our function. Y is equal to x plus 5 squared. And again, like this is where kids, they think that they think that they can do it in their head, and they make a mistake, right? They say, okay, we need to have x that is squared and a 5 that is added. But they mess up that the 5 needs to be inside the square. So it's not easy to just do on your own. These two functions are inverses. Now, if we want to determine whether the pair of functions are inverses, and we're looking at two different functions, f and g, we have two different options. The first thing that we can do is that we can just take one and do the inverse and see if we get over here, okay? So if we take this, we write it as a y, we swap x and y, that's not right, swap x and y, then we add the 15, then we divide by 6. I've got y is equal to x over 6 plus 15 over 6. Or, you know, x plus 15 over 6. Now look in here, are these two things the same? Because I know that this is the inverse of our original. 5 halves and 15/6 are the same fraction, right? If I think about this and I take out a 3, divide by 3, divide by 3, I would get 5 over 2. So these two things are the same. And that means that they are inverses. Now, they're inverses, which is fine. There's another really kind of cool trick, okay? If we have, and I'm just going to make one up here. If we have f of x is equal to x plus 5, And we have g of x is equal to x minus 5. These are going to be inverse functions. Function blue makes your number and makes it 5 bigger. Function yellow takes your function and makes it 5 smaller. So they're doing the opposite thing. These are function inverses. Now, if I do f of g of x, if I do composition, which we learned yesterday, what should happen is that all of the g parts should get canceled out by all of the f parts, and we should have only an x left over. Because if we take a 5 and we put it in f, it's going to come a 10, and then we put it in g, it's going to go back to 5. So here's how this looks like. We've got f, which is x plus 5. We've got g, which is x minus 5. The color's a little bit too hard to see. X minus 5. What happens when we do this? It's just minus 5 plus 5, and we just get x. So if you want to check inverses, okay, if you do the composition of two functions and the only thing left over is x, then you are going to be inverses. Okay? So for example, we found that these two were inverses. If I do f of g or g of f, it doesn't matter which way I do it. Let's say that I'll do f of g. That would be, take the f, which I have in red over here, that's fine. That would be 6x minus 15. And then take the g and put it in there. That would be 1/6 x plus 5 halves. Multiply everything by 6. That would be 6 times 1/6 would just be x. Multiply that. That would be 30 over 2 minus 15. And 30 over 2, this would be 6/6, which is obviously going to cancel out. 30 over 2 is 15, minus 15. Those are going to cancel out. The only thing left over is x, and that means that they are inverses. Now, to be honest, you're pretty much just going to try this every time. Do the inverse and see if what you get is over here. But you kind of need to know that this is a property. Okay, for example, a question on a test might say the composition of a function with its inverse is equal to what? Right? And so you would need to know just x, because all the extra stuff has become opposite of each other. They've canceled out. You've got nothing left but the x. So all that said, you could try this with all these questions, whatever. The last thing about inverses is to graph the function and the inverse, okay? Now for this function, let me write the function closer so that I can zoom in a little bit on the graph. My function, this one's easy to graph. This is a linear line. And so I can graph this. I can go to -4 and I can put a dot. I can go -2/3 is my slope down to, rise over run. So rise -2, run 3, rise, run, rise, run. And then I can go ahead and make my line. There we go. So there's my function, and perhaps I should make it blue. Because I've written my function in blue over here. Now, how can you find the inverse of a graph? Or what does the inverse of a graph look like? The inverse of a graph, again, our big thing with inverse is to switch our x and our y. And so if we take some points, like these points that I had here, and we kind of think about those points as being 0, -4, then that means that our inverse our inverse should have a point at -4, 0, because our inverse should have the opposite, right? So if this one has 0, -4, that's our original, then our inverse should have -4, 0. So that would be right here. If our original has the line right here, the dot right here at 3, -6, our inverse should have -6, 3. If our original function has a dot at whatever this is, 6, -8, our function should have, let's make sure we keep along the color scheme, -8, 6, which would be -8, 6. Now drawing this line, here's the graph of a function, which is blue, and its inverse, which is green. And the trick here is that a function and its inverse will always be reflected over this diagonal line. Okay? So notice how the green and the blue, they intersect at the diagonal line, that the green and the blue are kind of like mirrored over the diagonal line. That's because this is the line y equals x. And if what we've done is swap y's and x's, then that line y equals x is kind of like a very important line where y is the same as x. All right, so let's see that again. If we've got -x squared plus 6, -x squared plus 6, and this is our original function, okay? We know, first of all, that this diagonal line here is going to be a kind of mirror of our function. And we have a negative U shape that is raised up 6, okay? So we should be raised up 6. You know what? Let's just go to Desmos. Let's just figure it out. -x squared plus 6. Go to Desmos. -x squared. Can't use capital X. -x squared plus 6. I've got this point right here at 0, 6. I've got this point at 1, 5. So let's see here. Blue should be at 0, 6, 1, 5, -1, 5. And then, you know, I'm a U-shaped graph. You know how it goes. My inverse function would be the flip-flopped of all these points. That would be 6, 0. That would be 5, 1. That would be 5, -1. 6, 0, 5, 1, 5, -1. And so if I make that shape, and so here we have two U-shaped graphs they are inverses of one another. You can see how that red diagonal line y equals x is an important line where it's kind of reflected over that. Something that might be a test question is, what is the line that two inverse graphs are reflected over? And you would need to know the line y equals x. And we get a cool little shape here, right? I mean, this is kind of like a little heart inside here. But it's really just two U-shaped graphs that have been reflected over this line. And that's how they look. That's how inverses work. That's how the graphs of inverses look. The main idea is switch your x and your y. If you can find an xy coordinate, you just pick it and you switch it. That's the easiest way to go about doing it. As far as our functions go, you need to make sure you know how to do this process of switching your x and y and solving it. As far as verifying inverses, you can either just check it and see if they work, or if you do composition, you will be left over with only x. And again, a test question might be, if you do composition, what happens? And the answer would be, you're left over with just an x. That's inverses. That's how they look. That's how they go. Hope this